All right, working through the rest of section 9.4 here, we're looking today at probability of independent events and probability of dependent events once again. You worked on that in a card sort yesterday, and that's just, there's more to do with it. So we'll start off with a video that's two parts. So if we look down at this description here, we know now how to describe multiple events using set notation and how to determine whether an event is independent or dependent. So now we need to be able to calculate the probability of multiple events happening. This comes up all the time when we talk about insurances and how those rates are determined. So this is a pretty important mathematics skill to be able to understand how insurance works. So the probability of two or more events occurring together is called compound probability. That's a term you definitely need to know. We're going to watch part one of this video about independent events. We'll come back here and work on these problems next, and then we'll do part two and work on the second section. So if you want to read through these bold print questions first and decide just to see what it is you're looking for, that may be helpful to you. All right, so let's get started with that. Okay, so right now we're going to add this to your notes shortly, but this upside down U here is a certain kind of set notation that represents the intersection. So this means that this is like the overlap. So if you were to think of a Venn diagram with two different circles overlapping, this would be the part in the middle, the part where both of them happen. So that's a symbol that means intersection. All right, we'll stop there for now. Let's go back to the page we were working on, page 23, and take a look at these questions. Assuming that events A and B are independent, summarize the probability rule by completing the equation below. All right, so this gets to what we were just looking at on that screen. So what we said is the probability of the intersection of A and B is going to be the probability of event A times the probability of event B. All right, so what we're going to do is we're going to multiply the probabilities of individual events. And let's make a little note up here about what that symbol in probability notation is that this upside down U stands for the intersection. So that when we see that, we know what it means. All right, so question 2 here. Jim checks his weather app and sees there's a 15% chance of rain today and a 35% chance of rain tomorrow. What is the probability it will rain both days? So just pause here, go back to this formula and enter the things you know and see if you can come up with an answer. Okay, so the probability of the intersection of A and B would be the probability that it rains both days. And so to calculate that, we need the probability that it rains today times the probability that it rains tomorrow. Okay, so today's chance was 15%, so I'm just going to make that a decimal. And tomorrow's chance is 35%, so make that a decimal. And if you multiply 15% times 35%, you get 0.0525, and so that would equate to 5.25%. And that is the chance that it rains both days. Okay, so independent events, we need to multiply the probability of each one separately. All right, let's go on to dependent events. You should try that. Okay, you have that probability of green marbles already, so you should try that. Okay, so that if we have a dependent event, as we're about to see here, we need to think a little bit about how that sample space changes before we can calculate that. So, assuming the outcome of B depends upon the outcome of A, summarize the probability rule, completing the equation below. So let's do what we just saw there. Probability of the intersection of A and B for dependent events would be the probability of A times the probability of B after A, or you can say B given that A has already happened. Okay, so let's look at an example of that. Asia has a standard deck of playing cards, 13 of each suit, 52 total cards, just like we saw in that image before. Probability that she shuffles the deck, pulls 2 hearts, then a diamond without replacement. All right, so we've got 3 cards being drawn, right? Let me actually do it like this. Here, this is a little messy there. So I want to just draw those 3 cards. Card 1, card 2, card 3, and we're just going to end up multiplying all 3 things. Okay, card 1 is going to be a heart, so we're going to draw any one of the 13 hearts out of the entire deck. Right, there are 13 hearts out of 52 cards. The second card has to also be a heart, and we've now reduced the number of hearts by 1, so we have 12 hearts remaining. And we've also reduced the number of cards in the deck by 1, so 51. So this is B, event B after A has happened. Event C also is affected by event B and A because I've drawn 2 cards out of the deck now, so I only have 50 left to choose from. However, I do have all 13 diamonds remaining because I haven't drawn a diamond yet. These first 2 were both hearts, right? So I have 2 hearts removed, but I don't have any diamonds removed. So when I go to do this draw for a diamond, I have all 13 available. So I just need to multiply it out here. And if you do that on your calculator, what I would expect you to do is multiply 13 times 12 times 13 and then divide by 52 times 51 times 50. Now if you make a fraction bar first and you just put all of those components into your fraction, that'll get you there. And what I got for a decimal was 0.015. And so that's about 1.5%. Okay, so multiple events where the first one affects the next one affects the next one. That's where we have to consider how the probabilities change. All right, Roman and Mateo are completing a problem for math class. It involves pulling a red marble, then a blue marble without replacement. This is very similar to the one in the video. Roman calculates the probability of red and blue after red to be 10/20 times 9/19. Is Roman correct? Okay, pause the video here and write down a response that to explain whether Roman is correct. Okay, so the second event here is supposed to be a blue marble, right? So we draw 1 marble out of the bag, and that's a red one. And then we draw a second marble out of the bag, and that's a blue one. All right, well, the red marble, there were 10 reds out of a total of 20. And the blue marble, we now only have 19 because a red one came out, but we still have all 10 blues. That numerator doesn't go down because it wasn't a blue marble that we took out in the first place. So this is incorrect. Roman is incorrect. The second event is a blue marble. And the first event didn't decrease the number of blue marbles. Okay, so what we should have here is 10/20ths times 10/19ths. And if you multiply that out, make a big fraction bar, right? So this would be 0.263. And if you want to, you could convert that to a percent, 26.3%. So it's higher than what Roman calculated because Roman reduced the numerator too. So this would be what you would do if you needed a red and then another red. Because the red had come out, the numerator would have decreased. All right, so let's go on to the next page and look at a few insurance applications of this. All right, an auto insurance company, Insure Auto, is setting its monthly premiums and has created the following table based off of data they've collected. So you can see all of these probabilities for accidents per 30,000 miles driven. So if you are a male driver between ages 16 and 24, this is about a 17% chance that within 30,000 miles you will have an accident. If you are a female driver between 40 and 65, you only have a 4% chance, which is the lowest. Young males are the highest. Middle-aged females are the oldest, are the smallest. Then when you get older, the probability goes back up again, probably because your reaction time starts to decrease. So all of these numbers make a little bit of sense. Now, what's going to happen is for setting the prices, the insurance company is going to lower that probability by 2% if you have taken a defensive driving course because you've trained yourself to drive better. They're going to take off 5% if you own a car with crash avoidance features because you're less likely to have an accident if the car is beeping at you when you leave the lane or things like that. And you're going to add 3% if you're in a city with a population of more than 100,000 because it's more congested and there's a better chance of actually ending up in an accident in that situation. So not only do you use overall statistics, but the insurance companies will also take into account other circumstances for each driver. There are way more things than this. This is just keeping it simple. So let's go through the expected value of the following individual. So what we want to say, if we go back to our expected value formula, right, what we're going to do is multiply the probability of something happening times the value of that thing. So a 67-year-old man pays a $210 premium. Well, let's find where a 67-year-old man slots. So a 67-year-old man is going to be in this section here, right, 13%. And so we'll highlight his expected value that way. He has not taken a defensive driving course, so we do not subtract 2%. He does not have a car with crash avoidance features, so we do not subtract 5%. Lives in Collingswood, New Jersey, population 14,000. That is not more than 100,000. So we're not going to do any adjustments for this driver. We're going to go with that 13%. So 13% of the time, he is going to end up with an average payout of $1,100. So 13% of the time, the insurance company is going to lose $1,100 on this driver. This is coming from the perspective of the insurance company because they're trying to decide how much to charge him. And 87% of the time, he drives clean, and so they collect his $210. And they don't have to pay anything in that scenario. So multiply that out. You can pause for a second and do that. It comes out to $39.70. Okay, they hope to earn $25 profit per policy per month and pays $2,000 on average auto per claim. All right, so we'll keep that in mind as well. So let's keep going with this. Insure Auto sets its premiums on an individual basis. For each person described below, calculate the premium. All right, so what we have to do with this for both of these drivers is go back up to the chart, figure out where they slot, and then make the adjustments based off of their info. So Alonzo's a 22-year-old male. If you look at the top of the chart, that's a 17% chance of getting in that accident. Now we're also going to add 3% because he lives in a big city. So we'll add 3% because of the city. And we're going to subtract 5% because of the crash avoidance. All right, so if you go straight across there, now we're down to a 15% likelihood that this person gets in an accident. So if we want to earn an expected value of $25, where we would write EX here, I'm going to put a 25 because that's what we're hoping to the expected value to come out to. All right, now I'm going to take the 17%, no, not the 17%, the 15% times what that person is going to have to pay. And it says here they pay an average of $2,000 per claim. So 15% of the time, this driver will cost the insurance company $2,000. And that means 85% of the time, they're just going to collect his premium. And we want to know what premium they should charge, so we'll leave that as X. Right? That's what it says here. We want to figure out, calculate the premium that they must set in order to earn that money. All right, so if you multiply here, you're going to get a negative number, add it over to the other side, and divide by 0.85. All right, what you should get, and you can pause if you need to, what you should get here is that X comes out to $382.35. That's what they should charge him every month in order to break even on their predictions based off of statistics. Okay, Aaliyah is a 43-year-old woman who lives in Kirkland, Washington, population 91,951. Defensive driving course, does not own a car with crash avoidance features. So I want to do the same things here. I want to go through her probabilities. She is in that cell on the table, which is the lowest probability of getting in an accident. So she starts at 4%. We are going to subtract 2% because she has that defensive driving course. And that comes out to a total of 0.02. We do the same calculation. We set her at $25 profit is what our goal is. We're going to put her at 0.02 chance of having to pay out a claim of $2,000. And this is what the insurance companies do, just on a more complicated basis. There's a lot more to their equations, but they figure out what profit they want. They figure out how much each driver is going to contribute or deduct from their income. And then they set up their premiums that way. So now we have a 98% chance of just collecting the premium. So you can probably tell that for this driver, they don't need to charge as much because 98% of the time they're going to get that money. This driver, they were only going to get that money 85% of the time. So now if I go through this, multiply here, you get a negative number again, add it over, divide by 0.98. You can pause here before I show you that. All right, and what we should get here is $66.33. So, explain why Alonzo's premium is so much higher than Aaliyah's. We've already been talking about that, right? He is much more likely, statistically speaking, to have an accident. So, we must charge, oops, not much, must charge a higher premium to reach the desired expected value. And the same thing works in other kinds of insurances too. So if a health insurance company is trying to insure somebody, they'd want to know if you were a healthy individual or if you were a smoker, right? Because a smoker is more likely to need medical care than the non-smoker. So there's all sorts of insurance considerations like this where they try to assess how risky you are and how likely they are to have to pay for you. All right, last thing here is on page 25. Carrie's a 26-year-old woman. She's living in Melrose, Massachusetts, population 28,254, not taking defensive driving, nor does she have a car with crash avoidance features. Probabilities listed in the table, we already did that, right? So Carrie drives 30,000 miles each year for 5 years. Okay, so let's go through this. If C equals a crash, how would you write the probability of not crashing using set notation? So that came up before where we had that apostrophe. So we're going to do the probability of C apostrophe. That's how you show not the thing that it's saying. All right, so the probability of her getting into exactly 2 motor vehicle accidents over the course of 5 years. Well, if we have year 1, year 2, year 3, year 4, year 5, it doesn't matter which year contains the crash, just that there are 2. What we're going to say is that it's a 0.09 chance here, right, that she gets in an accident. If you look back at the chart, you can see that it's 0.09 for her, and it's 0.09 a second year. We can put these 2 0.09s in whatever 2 slots we want, because it doesn't matter which year that it happens. But that means that the other 3 years, she did not get in an accident, so that would be 91%. Right? So if you just multiply all that out, it comes out to 0.006, which is 0.6%. Okay, so that gives us a pretty good idea of how to do these independent and dependent probability problems and how they relate to insurance.